Okay, then inverse kinematics of sixth of industrial robot. We have already done quite a lot so far. You have seen my earlier video that basically dealt with the structure, kinematic structure of this Yaskawa GP12 robot. Okay, and most of the time the videos that I have floated, it clearly says how I normally follow with the symbols, and the way I have been doing so far is mostly trigonometric algebraic approach to solve inverse kinematics. Same I will be doing for this also. Okay, just see my earlier videos for this reason. Okay, so GP12 industrial robot is nothing more than a breast partitioned robot. Over here you see, this one is your wrist center. Okay, this forms the wrist center, and before to that is nothing but a 3R special robot. There is some changes in a standard 3R special robot, that is a positioning robot that we have discussed earlier. Okay, there is a little bit of change. Okay, just let us discuss the difference between that. So before to that, okay, so this is how a special 3R manipulator look like. Okay, it may be something like this. You may have x axis like this, y axis like this, and z like this. Okay, and this forms your origin of the workspace, and then first link that rotates like this is your theta 1. Second link, this orange one can rotate like this is theta 2. This is link length A2. This, if this is A1, this is A2, distance between two z axes. Okay, and then you have another link which also can go like this. So this is theta 3 and this is A3. Finally you have the end effector point which is here. Okay, so this can rotate like this, second one can go like this, third one can go like this. So these two z axes, so this one, that is Z2 and Z3, Z0, Z1 and Z2, Z0, Z1, Z2, and this is Z3, that is also the end effector Z. Okay, doesn't matter. So if this is Z0, okay, so this distance, as I have said, D1 can be equal to 0. This I have equated to 0 because I have placed this axis over here. Okay, it is equally good because you know this length is not going to change, and z of this, the z coordinate of this, if this is x, y, z, so z coordinate of this will simply have this as a constant term. This you can add later on also. Okay, so this you can add later on also. If this shows x, y and z, so z will be directly dependent on theta 1, theta 2, theta 3, a1, a2 and a3. d1 will appear as a constant in this. Okay, that you can eliminate while calculating that. Later on you can put that in, and this robot can further be mounted on a concrete block. Okay, and this forms the floor. In that case, this can even be placed over here. So you got it. So you have dealt already with this stick model of GP12 arm up to the wrist. Okay, but this is not GP12, I tell you, this is a standard 3R special manipulator. So let us see how a special manipulator like GP12 first 3 axis look like. So it is not like this. Okay, so how is it look? How does it look like? So it is effectively like this. You see, this was your first frame, this was your first frame x0. So you now you know I normally put it over here. So this is my new x0, this is my new x0. Got it? If this is your z0, okay, z0, so it is equally good. I have placed this origin not over here, I have placed my origin over here. So this is your first link length A1. So that is equal to 155. If you can see my data sheet, it comes very much over here. Okay, where this is 155. It is distance between first vertical axis and next horizontal axis. So this is Z0, this is Z1. Okay, Z0 and Z1. So it is shaped like this. So Z0 is vertically upward, Z1 is parallel to the ground surface. Okay, that is in x0 y0 plane. Okay, so that is there. So this is your Z1. So distance between them is link length 1, that is 155. That is the first one. Next comes from here till here. Okay, from here to here, that is 614 mm. If you check the data sheet, it is 614 mm. It is not standing like this, rather it is horizontal. Okay, so this is first pose of this robot, this is next pose of this robot, where this is horizontal, and you see this is 614 that will appear in this direction. So this is your second link length. Okay, if this is your first A1, this is A2. Okay, and angle, this link can go up and down like this. Okay, so this can go like this, so that becomes your theta 2. So first this axis is theta 1, this is your theta 2. Okay, so that is your second joint angle. This is your next link. Okay, then the third link. Third link is not directly like a straight line as it is shown here. From here to here you directly cannot go there. So how is it like? It is, if you see this, from here it goes something like this, then it comes like this. Okay, something like this, then it comes like this. So that is your rest center point from this. So this shape is something like this. Doesn't matter what is the shape of the link, it can be any shape, and finally it reaches here. These 2 point matters. Okay, so your link can be something like this also, directly like a straight line. Your link can be over here, if it is like this, it can simply be put like this. Okay, from here to here. Okay, that is what I have done. So your link length is 200 over here. If you see the data sheet now, 200, it is here. That is this distance from here to here, and from here to here, Swiss center, it is 640. Okay, 200 and 640. So that is 200 and 640. Okay, effectively, if at all this point is here, as in case I have drawn earlier, okay, if this is my end effector, 640 will appear here. Okay, 640 will appear here. Okay, just like this, and things would be very simple. But this time, and reference frame of theta 1, if this is the axis extension of this link, whatever is the angle of this link, I'll draw it here. So extension of this link, okay, theta 3 is measured about that. So this link can be like this, it can go like this. So theta 3 is measured with the extension produced from A2. If A2 is this length, if you extend this A2, okay, theta 3 we measure like this. Okay, it is angle between two links. Okay, so that is what. So over here what you see, this is the point which normally is as in case earlier. Okay, but this time as your link is shaped like this, okay, so you can directly say that your link is permanently like this. It has a theta 3 with some initial angle that is always there, that is a constant in home position. If this is your home position, okay, how a default robot would look like. So if this is your home position and this is your theta 3, you can start measuring from now and on. So if it is this angle, how this robot can move. Okay, so if this is theta 3, okay, so this permanent angle will always be a part of that. Got it? That means this is your initial angle. If you take 200 and 600, so you can directly find out what will be my theta 3. Maybe it may have some default angle, that is alpha if you take it. So how much is alpha? Alpha is this, that is tan inverse 200 by 640. Is it doable? So this is your permanent angle alpha. Okay, so that alpha is it in the home position, and then anything theta 3 it goes above that. Okay, so this is how this is constructed. So effectively we can create this robot something like this. What I was saying is something like this. You have A1 that is like this, you have A2 like this, and this is your effective A3. How much is that? It is simply this distance, and that is nothing but 640 square plus 200 square, square root of that, that is the magnitude. So it comes out to be 670.522. So that is the distance between these two. Got it? And this is the default angle alpha, that is tan inverse of 200 by 640. Got it? So it is default angle 17.354 degrees. Got it? So this angle is permanently there. It is not going to change with time. Okay, so now I can write my Yaskawa GP12 robot as A1, A2, A3. A3 is 670.522. So this is your A3, and it is at home position. This angle is permanently there, that is 17.354 degrees. Okay, if Yaskawa measures it this way, normally Yaskawa does this, so it effectively measures from the vertical. Okay, it measures like this. So normally this robot is in this position, and you measure the vertical angle, this angle. So you can get that vertical angle as 72.646 degree from vertical. Okay, effectively if this is 90 degree, so whatever is this reference frame from A2, if you create a line, imaginary line which is at 90 degrees, from there you measure this angle. So that is what Yaskawa does. So this is your theta 3 in case of Yaskawa. So that is what I have written over here. Okay, that you can quickly calculate as this. So in this position, in current position, that is rotating like this, so it is minus 72.646 degree. Got it? So that is what. So you know, understanding Yaskawa is a different thing. Okay, it measures like this, but by default we'll solve it the way we do it. Okay, so we take this as an angle alpha, we'll call it theta 3 alpha, that means theta 3 plus alpha. So whatever is my movement, if I am moving by theta 3 angle for this link theta 3 A3, okay, so whatever is my angle theta 3 alpha will be theta 3 plus theta 3 alpha, theta 3 plus alpha. So effectively you have theta 1 for first joint, theta 2 point second joint, theta 3 alpha, that is equal to theta 3 plus alpha, that is the third joint angle. So these are the three joint angles, and these are the lengths. Now I'll do kinematics of this, both forward and inverse. Okay, so now, yes, yes please. There is no offset, everything is a in sagittal plane. If you take section of this robot, so this is always in a sagittal plane. Okay, all the links, all the joints, if you can create a symmetry plane like this plane, this will pass through the center line, and all the links will be on that axis. There is no offset, there is no offset. Got it? So whole of this is in a plane. Okay, so there is a situation when this link is in plane, whole of this set is in a plane, so there is no offset. Okay, so that is not just an assumption, it is the way this robot is. I told you that day, there is a link which comes out, this link basically, this link, this link comes out of the plane and goes back to the plane. Okay, so I normally take that out from this system. Okay, and I have put everything on the plane, because same distance it comes out and same distance it goes back. So I simply can discard that I have explained earlier in my previous lectures. Okay, so now we'll go to, assuming that everything is in a plane, I have drawn this figure. Hope you can understand this. Now I'll simply tell you. So now this is your theta 1, that is the first link, 155 length. It moves in this is theta 1. It is on the plane xy. This motion is there. This link always lies on that plane. Next is this theta 2, that is A2 creates from the plane. This is the angle which is measured from the plane xy. From the plane xy, it measures by an angle theta 2. Okay, and then uh, this is what is your theta 2. I have simply extended this and I have written theta 2 over here. And you know, in case of the link that we have created, okay, let me clean it off now once again. Okay, so this angle, this is a default angle for this link, and alpha is the default angle that is always there. On top of that, if at all you are moving by an angle theta 3, it becomes theta 3 alpha, that is the new angle of this link, and that is equal to theta 3 plus alpha. Clear? Okay, now going back to my system. So now this is your theta 3 alpha, this is your theta 2. Now whole of the system looks like a 3R subset that we have done earlier. Let me just verify that. Okay, so how much is this vertical distance from here to here? That is A3 sine theta 2 3 alpha. If this is 3 alpha, this is theta 2, so it will be equal to sum of all these. So it will be equal to theta 2 plus theta 3 plus alpha. So this is correct. Now, how much is this distance? This much. This is simply this much, and that is A2 sine theta 2. A2 sine theta 2. So these two are done. So effectively, Z of this. So how much is whole from here to here? That is equal to Z. So Z is equal to D1 plus D1 is this that I have discarded right in the beginning. Okay. So this becomes equal to 0 for GP12. Okay, you know the reason why I can consider it later on also. So it is no point taking that complexity over here, so simply discarding this. So effectively how much is Z? It is equal to A2 sine theta 2, A3 sine theta 2 plus theta 3 plus alpha. Got it? Okay, now how much is X? Now how much is X? We have done it earlier. So X will be simply, if you take this distance, cos theta 1 of this is X, sin theta 1 of this is Y. Okay, and how much is this? This is A1 plus this. So A1 plus this, cosine of that is X, clear, and A1 plus same sin A of that is Y. So whole of this distance, okay, cosine and sin A is X and Y. So hope you have got till here. Yes, very good. So okay, so now we have done the forward kinematics part of this using simple trigonometrical projections. Okay, so once again, this is A1, this is projection of this. So this is A2 cos theta 2. Then how much is this? Same is this, that is A3 cos theta. If this is sine, this is cosine, and same is this. So I simply can take sum of that. So it is this much. Okay, and cosine of that and sine of that. That is what is this. So by projection, I can simply obtain x, y, and z. Okay, so hope I have got till here. Now I'll simply do the rest of the things. Now theta 1 can be quickly obtained as tan inverse y by x. Done. Tan inverse y by x, that means theta 1 is found out. I know this now. Okay, using this I can find what? I can find x and y virtual. Okay, so what is that basically? So if you what I intend to do now, I want to take my help of this subset. Hope you got what I am trying to get. This is the subset which is known. If somehow I can get Ex dash, that is from here to here, that is Ex dash, and here to here, that is Ez dash. If somehow I can get this and this is a 2R manipulator solution for which is well known, that is elbow up and elbow down solution. You have done it earlier. Okay, so I can use that. So I am trying to get to that. Okay, so I am trying to find out Ex dash. So how much is Ex dash? Is simply x by cos theta 1. Cos theta 1 is known now. Okay, x by cos theta 1 minus a1, minus a1 is this, this, clear? So that is what is your Ex dash. Done. First part is done. Second part. Okay, second part is simply Ez dash. Ez dash is from here to here, that is height from C to D. Okay, you can quickly evaluate it from here, and that is nothing. Ez dash is effectively this, because you don't have any D1 over here, so it is simply this one only, A2 sine theta 2, A2 sine theta 2 from here to here, and A3 sine theta 2 3 alpha, this one. Okay, so you quickly can add it. So now you have got what? You have got Ex dash and Ez dash. So now you know the coordinates of this 2R subset. 2R subset. Okay, 2R subset. For this you now know the coordinates. What is that? That is Ex dash and Ez dash. So if I know these two, that means this and this, I can quickly obtain what? Theta 2 and theta 3 alpha, not theta 3, it is 3 alpha. Okay, so we'll try to do that now. I can quickly write it as this. Okay, this is a simple equation of a 2R subset. Okay, this is equivalent to a 2R link with link 2 and 3 in plane x dash z dash. So z dash is z only. So this is z dash. Okay, which is rotated about z by an angle theta 1. So this plane, if I can see this is rotated by an angle theta 1 about z axis. That is quite clear. So this is in this plane. So I know what? I know this link now. Okay, this link now. Okay, so using that I can quickly obtain my 2R. This is analogous to 2R manipulator. Okay, that is what I have written here. So you can quickly use the same solution what we have done earlier to get this. Okay, and how much is theta 3? You can subtract theta 3 alpha, from theta 3 alpha you can subtract alpha, that is the permanent angle, and you can get theta 3 directly, how much that angle actually have turned. So that is minus of that. Okay, so it has how many solutions right till here? So it can have a solution which is like this. Okay, going to this point, other solution will be something like this. So this is elbow up solution, this is elbow up solution, and this is elbow down solution. This is elbow down, this is elbow up solution. Okay, and at the same time this link can go behind by 180 degrees, and from there you can come back to this point, and again you will have elbow up and down solution. That is effectively 4 solutions will be there. But in case of Yaskawa, you know, you cannot take your robot like this. This link cannot rotate that. You just see this robot, it can rotate downwards, but it cannot go this way to much higher angle. Okay, if this link is shaped something like this, obviously there is some physical hindrance that will be there in most of the position which is possible kinematically. Okay, so this link cannot go this way, so only possible is downward approach. That means elbow up is always possible. Okay, elbow down is not possible. Oh sorry, elbow down is possible, elbow up is not possible. So it can take any angle downward, but it cannot take it upward. Okay, so that is what physical limitation of any robot it is there. Okay, and that is what is limiting Yaskawa also. So now we know 3R spatial manipulator inverse kinematics. That means we have calculated, if I know somehow this point, what is this point? This point is basically wrist center point. This we call it as, this is wrist center, wrist center point. Okay, so this center point, if this is known, I can calculate theta 1, I can calculate theta 2, I can calculate theta 3. Three angles I can calculate. That means if I know this point, I can know rest of the points. So only thing that is remaining with inverse kinematics of Yaskawa GP12 robot will do the rest part of this now. So we have done the first three joints. We know now, if we know somehow wrist center point, I can calculate the rest of the three. Okay, now I'll do the rest. Okay. Okay. So this is just a quick verification of 3R for Yaskawa GP12 robot, how to do it. So this is the structure, how it looked like. Okay. So if I know the end effector point, if I assume this point is given, this point is given, this is nothing but wrist center point. Okay. So this is your first point, this is your D1 that I have eliminated. So this is the point which interests me now. Okay, so this is how this robot is structured. I know this point directly by adding the kinematics. Okay, so using that, I have simply used the MATLAB code which looks like this. Okay, I have taken input as x, y and z. This is in sagittal plane, so there is no y axis changes. This is your z0. So this is how you calculate the first point. Let me just zoom it out. Okay, so this is your D1. D1, I won't use it. This is A1, this is A2, this is A3, basically square root of 640 and 200. So this is how I quickly calculate in the code itself, and alpha is equal to tan inverse 200 by 640. That elbow, if you remember, this was 200 and this is 640. Okay, so this is the elbow and that is your alpha. Okay, so that is what I am calculating here. And theta 1, if you remember, theta 1 is simply y by x. So ex dash and ez dash. So I have just pinned my equations which was there earlier, which I have derived just a moment back. Let me go back to that slide if you remember this. So this is your theta 1 and then this is your theta 2 and this is your theta 3. Let me just wipe it off to make things clearer. So this is your theta 3. Okay, this is what same thing I have put that on code. Okay, so that I can later on play with any value of x, y, z and I can calculate that. So just one value, as I know it cannot go like this, it only possible solution is something like this, elbow down. So I am eliminating the elbow up solution here, and that is the negative sign of theta 3 is only that I have considered. Okay, because physical robot cannot go that way. So theta 3 and theta 2 can be calculated, and for Yaskawa I get something like this, theta 1 0, theta 2 90, that is this. So for any given position xyz of this, I can calculate theta 1, this is theta 2, this is theta 2 and this is theta 3. Okay, so those angles can be quickly obtained. Got it? So this is first three solution, first three angle solution. Now let me move ahead and do the rest. So you know this point we have done. I'll try to, given this end effector point x, y and z, I'll try to find out this point and get theta 1, theta 2 and theta 3. Okay, and using the orientation of this, I'll try to find out theta 4, theta 5 and theta 6. So any rest partitioned robot, as you know, most of the industrial robots are rest partitioned, as in case this one also, this is rest partition. Yeah, it has rest here. You can have a robot like this, which is little bigger. Okay, it has rest over here. So any robot like this which has last three axes as a spherical joint can be treated like a spherical joint, or intersecting axes, they can be partitioned at the rest center. Okay, so inverse kinematics for those I will be discussing now. This is what is rest center point. Okay, your inverse position analysis, inverse orientation analysis. So this can be the problem of 6th inverse kinematics can now be decoupled to two different problems. First is, given this point, rest of the system is position kinematics that I have done, and given the orientation of this, I can find out 4, 5, 6 angles by using wrist solution. That I will show you now. Okay. So now same what we have done earlier. Okay, just how we did it, let me come back to that once again. So given a robot end effector point, this is given x, y and z. Okay, that means you now know the position vector from here till here using your standard approach. Okay, you already know the x, y, z, that means O6 will be equal to xi plus yj plus zk. So this is what is your position vector. You can quickly write it as xyz1 if you write it this way in matrix form. So that is what is known. Okay, so this is very well known. So you now know 006 is now known. Okay, this is known because, and you also know d6, that is the distance from wrist center to the end effector. What is that? Let me take you to that slide once again. Okay, from wrist center, let me clean it up also. Okay, hope this much is enough. So from wrist center point to the end effector point, so that distance is known. Over here it is 100 without the gripper. You may have a gripper that is attached after this. In that case, from here to here will be having some distance. In my case, the gripper which is fitted here, this distance was 235. Okay, this distance from wrist center, this is 235 and this is 100. Okay, in my case, the situation which is given here. Okay, so this is that distance d6. Got it? So let me come back to d6 now. So things that are given. So this is given. D6 is given. Now we have to find out this. I am interested to find out this. You know why? Because that is the rest center point. If I know this, I can find out theta 1, theta 2 and theta 3. First angle, second angle and third angle. Okay, that we can find out. So we'll try to get what? We'll try to get this rest center point from O. Okay, so how that can be done? Because you know now what all things that you know x, y and z. We are doing inverse kinematics, so we know the position, we also know the orientation. In case of industrial robots, orientation is given as roll, pitch and yaw angle. Roll, pitch and yaw angle. So overall this information is there with you. So provided you know roll, pitch and yaw, can you calculate the orientation of this? If I tell you this link is rolled by this much degree, pitched by this much degree and yaw by this much angle, so using Euler angle solution that we have done earlier, we can quickly find, we know there are three rotation. One is with respect to x-axis, y-axis and z-axis. So those three rotation, if you just multiply them, you can get the rotation matrix for this, that is 0 or 6 is known. That means given roll, pitch and yaw, you can quickly calculate 0R6. Okay, that we have done Euler angle RPY solution. Okay, so that is what is done. So that using that you can quickly get the orientation of this. Now this is also known. 0R6 is known. So using the informations that is there with us now, we'll try to find out the wrist center point. How that can be done? First we express the magnitude of this vector, and this vector initially was something like this. Z is now like this. Unit vector Z, if I call it D6, initially it was something like this. This is your W. It was like 0, 0, 1. It was aligned with Z axis. It was aligned to Z axis because you know there is Z axis which is attached over here. Okay, so that is Z axis. If I want to rotate it, rotate this vector by this orientation angle. Okay, so this is my vector. I have rotated with this. So I got what? I got a unit vector which is like this. So this is what I have obtained. Okay, this is what I have obtained. I have obtained my unit vector W like this. Unit vector and effector Z axis. Okay, and already it is associated with the magnitude D6. So if it is an unit, yes, Bridges, yes, please. Yes, just a sec. You can rotate a vector using what? Using your rotation matrix. So if this is your rotation matrix, you already know your vector. What was that vector? This effectively is Z axis which is pointing like this. So I want to get this vector. Okay, initially it was 0, 0, 1 because it is pointed towards Z axis. So it is 0, 0 and 1. A vector, if it is 100% pointed towards Z axis, in the matrix form it can be written as 0, 0, 1. So this is my vector. Now I want to rotate this vector by how much? 0R6, because I know this vector is now to be oriented as my end effector is oriented. Okay, so I know the rotation matrix of my end effector. So I'll quickly use my rotation matrix 0R6 and apply that to 001. So this is my initial orientation. After rotation, it will have some orientation. This is going to give me some orientation of my vector. And where will be that oriented? It will be oriented the way end effector is oriented. Is it not? Because this is rotation matrix for end effector. How you have obtained it? By the given information, that is R, P and Y, from where you have obtained 0R6. Okay, 0R6. This is the 6th point. So I know the orientation using roll, pitch, yaw angle. So I have obtained 0R6, multiplied that with my given vector, that is Z axis vector. Z axis is now rotated using 0R6 and I got a vector which is like this. Now I have to get the magnitude. So a vector multiplied with its magnitude gives me the actual vector in that direction. Is it not? Any vector v, any vector v is basically what? It is unit vector along that direction into magnitude of that vector. Is it correct? You know this? So that is what I have done. This is magnitude of that vector. This d6. This we know the distance. So that is d6 is the magnitude. This is now unit vector along that direction. So this is the unit vector. So that completely gives me this vector. Okay. So this is small thing. Yes, it is not that difficult though. So you have to get into your brain that any rotation matrix can be used to rotate a vector also. So this was your original unit vector. Using rotation matrix, I got to the unit vector which is directed like this, and multiplying with the magnitude, I got the actual vector which is like this from here to here. So now what is this? This is this vector. Okay. So now this plus this should give me this. Is it not? That is quite clear. So using that vector equation, I have obtained this. Okay. So this small equation tells you a lot. This quickly gives me the risk center point, this point. Okay. Risk center point is obtained. So how I have obtained? This was given. Orientation was given. So how much is this? This is d6 into rotation matrix 0 or 6 into unit vector z, because this is z. Okay, so this is your vector. So this, yes, it is in home position. So if you multiply with the rotation matrix, if you multiply that with the rotation matrix, initially it was like this 0 0 1, it will go to this. So a vector, if it is not rotated, a vector which is like this, if it is not rotated, it will be aligned with this axis, is it not? Z0. And how will that be? It will be 0 0 1. It will be projection of that along x 0, along y 0, along z 100%. So that is what is end effector orientation. It simply tells you the orientation of the final vector. Now I have rotated. Okay, so that gives me the vector which is in. Why it should be 0 0 minus 1? Initially it was like this, no? This is the initial position. Home position is not like this. Home position is this. Got it? Got it? So home position is always like this. If it is like this, projection is 0 0 1. Is it not? If it is like this, it will be 0 0 minus 1. Is it not? 0 0 minus 1. But it is not like this. Home position is always like this. That is aligned with Z0. Got it? So yes, now we'll move ahead. So now you know risk center point. Using that, what you can do? Risk center point, if you know what you can do, you can get what? Theta 1, theta 2, theta 3. If I know risk center, just now I have told you first three axes can be solved. That we have done a moment before over here. This is what we did, no? If risk center point is given, this was my robot. Okay, this was my robot. If I know this risk center point, I can get theta 1, okay, that is the angle about this, then theta 2 and theta 3. That is what we did just a moment before. So same. So now that I could obtain this, that is rest center point, okay, this is obtained. I can calculate theta 1, theta 2 and theta 3. Okay, so I can immediately obtain theta 1 to 3. Now what is remaining is theta 4, 5, 6. That is theta 4, this is theta 5 and theta 6. That we can do later on. First, don't get into that. Just let me finish this first. So now, you now know the end effector orientation using roll pitch yaw angle that is given. You know x, y, z and roll pitch yaw is given. Okay, so you now know 0 or 6. Okay, orientation of this point is known. Okay, now that you know theta 1, theta 2, theta 3 using this step, you now know theta 1, theta 2 and theta 3 because you have obtained the base center point. So if you know theta 1, 2, 3, so now you also know the ds parameters of first three links. Okay, that means you can obtain the rotation matrix till here. You do forward kinematics, okay, you can find out 0 to 3 transformation matrix using A1 0 to 1, A2 1 to 2, A3 2 to 3, because you have DH parameters in hand. Okay, DH parameter is basically defines the structure of the robot. If you know the DH parameter, you know the joint angles, That means you can calculate 0 T3. What is this? This is basically 4 cross 4 matrix with rotation part here and position part over here. That will give you position and orientation till the wrist center point. Okay. So now what we can do is, let me just write down once again this much. A simple thing that I want to write so that you can get quickly. So basically 0R6 rotation matrix and effector will be equal to 0R3 3R6. Is it not? Any matrix can be written like this? Yes or no? Yes. Okay. So now I have obtained using theta 1, theta 2, theta 3, I can obtain the rotation matrix of this using forward kinematics. That means this one I can obtain. This is given over here as an input. I can find out rotation from rest center to this. Okay. Next big rotation, 3 rotation, that is a spherical joint rotation. Okay. So that is what I am trying to get now. Okay. So 3R6 will be equal to inverse of, so you can write inverse of a rotation matrix is equal to transpose of that. So instead of writing inverse, I can quickly write it as transpose. So that is what I have done here. So this gives me 3R6. 3R6 is rotation of wrist center with respect to this frame. Is it not? So this frame with respect to this frame is this. That is the rotation only. Okay, that is the rotation only. So now I'll try to find this out. And you now know what is this? 3R6. Once it is obtained, okay, we'll try to do rest of the things. This is just an explanation of what I have said just now. 0R3, 3R6 is 0R6. 0R3 inverse is equal to 0R3 transpose. Okay, so 0R3 is equal to 0R3 inverse, 0R6 is equal to 0R3 transpose into 0R6. So it is exactly the same, need not any explanation here. Okay, so now any this type of rotation, we can recall our spherical wrist transformation. I have simply copied that here. I have simply copied that here. Okay, and I have written it once again, same matrix 3R6. This is for the spherical wrist. If you remember, I have just copied that here. This is in my earlier video. You can quickly check that. So this is your rotation and this part is your translation. If this is D6, so this D6 is here. Okay, this is D6. Okay, so from point this, orientation and displacement is given by this, displacement by this is orientation. And what is this? It is 3R6, is it not? This is 3R6. This 3 cross 3 matrix is nothing but 3R6. So this is your orientation. Now this is how I can write this. So this is your 3R6. Okay, and this is what you have obtained in my earlier slide. This is what we have obtained, 3R6. 3R6 is now known. Okay, so this can be equated to this. Okay, so 3R6 is this. Okay, and now I want to solve this. So if this is 3R6, this is how it look like. Okay, this is how it look like. So if each of these elements are known, magnitude of that is known, that means this matrix is known, means the values are known. Okay, 1 1 1 2 1 3 3 2 1 2 2 2 3 3 1 3 2 3 3, all the values are known. If the values are known, both the matrices are same. Okay, if both the matrices are same, just see it carefully. Can we obtain all the angles? We have done it earlier also. Just check one by one. If you just can figure out this too. Okay, if you divide this by this, that means S4 S5 by C4 S5, it gives you tan theta 4. So theta 4 will be equal to tan inverse S4 by C4. It can be written as in arc tangent as arc tangent A tan 2. You know why? So now this is equal to simply Q23, Q23, Q21, 22, 23, this S4 and C4. So this gives you theta 4. Okay, this is what is your theta 4. That is what is written here. Okay, now moving to next angle. Moving to next angle now. Okay, theta 4 is obtained using this value. Now I will try to get to some other angle. Okay, so weaker one should be attacked first. A tan 2. I hope you have seen my earlier lectures. Okay, just see that once again. So this is A tan 2. A tan 2 is a special solution which eliminates the quadrants all, which gives you all four quadrant solution. If you remember, this is quadrant 1, this is quadrant 2, this is quadrant 3, this is quadrant 4. Okay, if you get plus in x and plus in y, so you should get all the solution which is here. Minus in x, minus in y should give you somewhere over here. It should not give you same solution. Why? You see, tan inverse y by x will give you same value. If it is here, it is here, it doesn't matter, because minus minus will also give you same value. That is what is eliminated by taking a tan 2 solution. This is discussed in my earlier lecture, that you can go back and see that. Okay, so that is what, that elimination is done using a tan 2 solution. Okay, so it is nothing but tan inverse, but it is a conditional tan inverse which eliminates all these conditions carefully. It checks which quadrant we are in and gives you the appropriate angle of this. Okay, it will give you plus plus, it will give you solution in this quadrant. If it is minus minus, it will give you quadrant this. If it is x is negative, y is positive, it will give you solution in this. If x is positive, y is negative, it will give you solution in this. That is what is 8 and 2. Got it? I have explained it very much in detail. Just go back there. Okay, so this is nothing but tan inverse for the time being. Even if you don't know that, you can later go on to that video. But for the time being, it is just a tan inverse. Okay, for the time being, those you don't know this, hope you have to go through that later on. Okay, you will have to go through that later on, but for the time being it is just tan inverse. Now let me go to this one. Okay, using these two, what we can obtain. So if I square and add these two terms, what I will get? C4 square S5 square plus S4 square S5 square. So this is equal to S5 square, I can take common, C4 square plus S4 square. So this is equal to 1. So it is equal to S5 square. If I take square root of this, so it gives me S5. Okay, so this gives me S5. From here I can obtain S5. This is C5. Again, sine theta 5 and cos theta 5. Okay, so I can get theta 5 as this. Okay, so theta 5 is equal to tan inverse of sine theta 5 cos theta 5, is it not? So this can be written as this. Done. Okay, now let me go to one more solution, that is the last one, that is theta 6. How do you obtain theta 6 now? So you have to keep, don't see the puzzly part of this matrix. Okay, see the one which is very simpler. So I have attacked the weaker part of the matrix. Now you just see this one. Okay, can you, what you can obtain from this? What you can obtain from this? if I take this divided by this, that means S5 S6 by minus S5 C6, it will give you what? This gone, so you got minus S6 by C6. So now that is what is theta 6. So it is tan inverse S6 by C6 is equal to theta 6. You have to take minus because it is minus here. Okay, so that is what is done here. So theta 6 can be obtained using these two terms. So theta 4, theta 5 and theta 6 can be obtained. So it has many number of equations, you see, and just three unknowns. Theta 4, theta 5 and theta 6 unknown is there. But how many equations are there? There are total 3 cross 3, that is 9 equations can be formed. Okay. So it is redundant, that means solution does exist. Okay, there are multiple solutions also. Okay, what is that multiple solution? I'll just demonstrate that now. Okay, so that is for the reason why theta 5, if I'll just show this video here. Okay, I'll just zoom it out a bit now. Okay, so this is your robot. Okay, so if it is like this, okay, it is pointing to this point, and you see same position I can reach how? In an alternatively I can rotate theta 5, this is the angle, theta 4 by 180 degree. Okay, and it went up, I went down and I reached to the same place, no change, is it not? So that means two solution exist for this spherical wrist also, that is theta 5 can go like this. Okay, somewhere like this, and you can again reach to the same point. That means this angle theta 4 can be this or 180 like this, and accordingly theta 5 will be upward or downward. Okay, so you got me what I am trying to say. Okay, now coming back to my slide. Okay, coming back to my slide. So this is what is the alternative solution that quickly gives you a alternative solution, the one that I have explained. That means theta 4 is 180 degree apart. Okay, in this case whatever theta 4 you are getting here, you will get theta 4 in opposite direction. Okay, that is alternative solution for this. So these are the two solutions for the rest, and for rest of the three, how many solutions you had? 4. Okay, 4 into 2, that is 8 total solution is there for this type of robot. Okay, so 4 for the first 3 axes, 2 for the rest of the them. Okay, for each of them you get 2 solutions, so it is total solution is 4 cross 2, that is equal to 8 solutions are possible for this type of robot. That's all. Okay, so overall if you know x, y, z, rpy, okay, roll pitch yaw, you can get theta 1 to 3 as a first solution, position solution. Next 3 can be obtained like this using the risk solution. That's all. Okay, so if at all you have any query, you can definitely come back.